get started on the other stuff. So this is the 625 classroom meeting. We're going to talk about chapter 25 today. But before we do that, are there any questions on the chapter 4 material, atoms, protons, neutrons, electrons, isotopes, ions, that kind of thing? You can unmute yourself if you have a question, or you can type it in the chat. Abby says, can I review Amos? You mean atoms? What is Amos? The AMUs. Oh, okay. So basically, it's just really simple. Plus, 1, 2, 3, that kind of thing. So inside the nucleus, you have, your protons. So if you're a hydrogen atom, you got one proton and you have one electron, and they're buzzing around. So the electron has 0 AMU. An AMU is an atomic mass unit, and it basically is a very, very small number in grams. But rather than write that really, really small number, we just give it the name AMU. So what is an AMU? An AMU is the mass of a proton, an atomic mass unit. So protons weigh 1 AMU, and inside the nucleus, we also have the neutrons, and they also weigh 1 AMU. So when you're talking about the atomic mass of something, you're talking about the protons and neutrons, because the atomic mass is every single, what we call nucleon, or basically any particle that's in the nucleus, and it has a mass of 1 AMU. Now that's an actual number in grams. It's just, rather than writing it over and over and over, because it's, a big ugly number, 1 times 10 to the negative 24th grams, they just shortened it to AMU. We do this a lot in measurements. A good example of this is what we call an AU. So if you're interested in how far away something is in space, well, the distance from the sun to Earth is 1 AU. Now, it's something like 90 million miles, but again, it's a number that's measured in other distances, but we're just giving it a new name. It's like the mile, right? The mile is 5,280 feet, right? But they just took this and called it a mile. So that's all AMU is. So then if you're looking at an atom, and they're talking about, how many protons, neutrons, electrons it has. So if they write it like this, like 13, this is your atomic mass. So then they might also write it like this, where the top one is your atomic mass and the bottom one is your atomic number. So the protons is always the atomic number. That's 6. The charge is up here, but there's no charge, so we just assume that's 0. Carbon doesn't like to have a charge. Erase that. Let's do this. There we go. Carbon normally doesn't like to have a charge. So that means that the electrons are 6, because they got to add up to be 0. And then the neutrons, oh boy, the neutrons are going to be the protons plus the neutrons equals 13. So 13 minus 6, you can just kind of do that. And you have 7. So, and then this is 6. If you want to know the mass, these things would all weigh 6 AMU. These things would have 0 AMU, and this would be 7 AMU. And that's where the 13 AMU come from. So it's just a really, really, really small mass. So we just gave its own name, which is a lot, you know, how we do a lot of things in measurement systems, you know. Back in the day, they had barrels. So they would have a barrel of wine, you know. And, you know, there's a certain amount of gallons that would fit in these barrels, and those were called butts. So if you ever heard of a butt load, so it's an amount of wine. So again, it's just a name that people made up. Horses have hands. And again, what's a hand? Well, it's an inches measurement. It's a foot measurement, but it's just specialized to horses, you know? Same thing with the ton. You know, all this stuff came from like practical measurements. That's what the metric system was designed to do away with, was to standardize these measurements, because everybody had like different specialized measurements. Did that answer your question? Okay. What else you got? There wasn't a lot of stuff that you probably didn't already know in chapter 4. So maybe the history of the atom stuff, but most of you guys already learned about protons, neutrons, electrons. So if you guys don't have any questions, we can just move on. There's lots of resources in the module, so I'm guessing most of you guys were able to kind of get through really quick. Today's stuff you're going to have a lot of questions on, so it's kind of a heavy day. Okay, let's jump into it. So we learned about these things called electrons, and they're very important because it turns out that most of the chemistry that we see in our daily life is caused by electrons. The protons are just sitting in the nucleus, not doing much. The neutrons are just sitting in the nucleus, not doing much. There's a whole area of chemistry called nuclear chemistry that deals with what do the protons and neutrons do, and we'll go over that at the end in the second semester when we do nuclear chemistry. But for the most part, all of the chemistry that we know of is moving electrons, and so understanding the electron and where it is and what it's doing is very important for understanding the world around you. So they wanted to know about electrons, but the problem they had was electrons were notoriously difficult to observe. And the reason for that is they didn't behave like bullets, little specks, most of the time. They behaved like waves. So if you think about a wave at the ocean, it's this big, long column of water that is made up of little individual pieces of water. So it's moving in a certain way, and it has energy and it has force. But how does it deliver that energy? How does it deliver that force? And so it was kind of difficult to understand why electrons were what we call a wave-particle duality, meaning they traveled as waves, but when they finally got to their destination, they would hit like a bullet. So imagine you were in the ocean, you saw a wave coming, and then all that wave just suddenly turned into a little ball and hit you in the face. That would be very weird, but that's how electrons work. So at the same time as all this is going on, everyone is trying to understand light. What is light? Light obviously has energy. It makes things hot. It, fuels all the life on the planet. And so what is light? And so for a long time, people were trying to understand light. Isaac Newton was the guy who gave us the visible light spectrum, the red, orange, yellow, green, blue, indigo, violet, because whatever the heck indigo is. But that was, Newton. He wanted to add that color in there. And basically what they found is that light moved like waves. And there are a couple different types of waves. There's what's called longitudinal waves and drawn a blank. Either way, compression waves. And light appears to be this very interesting thing where it's an excitation in the electric field, and this excitation in the electric field causes an excitation in the magnetic field, which then causes another excitation. So it's this wave that exists in both the electric field and the magnetic field. That's why electricity and magnetism are so closely linked together, because they're basically kind of opposite planes of the same kind of field. So light is energy that moves in this wave pattern. And when they started exploring more about electrons, they found that they were moving more and more like light. And they would interact like light, and they would give off light. A great example of this is Einstein is able to figure out, why does metal glow when you get it hot? Well, he came up with his first Nobel Prize, which is called the photoelectric effect. And basically inside the atoms, the electrons are moving around. And when they move around, they change how much energy they have. And because they're so small, the only way for them to gain or lose energy is to absorb it as light or to emit it as light. So electrons must be closely related to light. So if we're going to talk about electrons, and we're going to talk about how they behave like light and how they give off light, we need to really understand wave functions. So let's go ahead and get into it. Now, you may have heard these words before. For the case of light, the most important ones are wavelength, frequency, and speed, because with those we get the energy. Amplitude is not really as important with light as it is with sound and other types of waves. So what exactly are we talking about here? Well, if we think about a wave as this kind of like sine curve down here, the amplitude is the height of the wave. Transverse wave, longitudinal wave, or compression waves, transverse wave. Oh, didn't think earlier. So a longitudinal wave is like a compression wave, so like a slinky or like a spring, and sound moves through the air in what's called longitudinal waves that kind of compress the air as they vibrate through the air. Light moves in what's called the transverse wave, which is like a sine wave, for those of you who guys are good are in higher level math classes. But basically, it looks like that, where you have this kind of, up and down motion. Woo, woo, woo. And so the height of these humps is what we call the amplitude. In light, amplitude is the brightness of the light. And the way that we increase and decrease amplitude is we really just kind of lay light on top of each other. So if you're looking at an LED that's really bright, it just has a bunch of different little pieces that emit light, and it kind of focuses that in one spot. For sound, amplitude is a volume. When you think about speakers, when you are increasing the volume of it, all you're doing is increasing how much the speaker vibrates back and forth. This causes the height of the compression of the longitudinal wave to basically get bigger. So the height gets bigger. But it doesn't really have much bearing on light. other than brightness. So what's more important is what we call wavelength. And for wavelength, this is going to be the distance between the peaks. And we give it the symbol lambda. You may have seen this symbol in the game Half-Life. It is not the Half-Life symbol. It is lambda, which is wavelength, which has very little to do with Half-Life, but you know, they thought it was a cool symbol, so they put it on there. But as you can see, we have different distances between the peaks of the waves. And this is what we call wavelength. So if you've ever been to the ocean, sometimes the ocean can be difficult because the waves are really, really big and they're tall, but they don't come very often. There's a lot of distance between those waves. And then sometimes it can be annoying at the beach because even though the waves aren't very big, they just keep crashing. So it's kind of hard to sit on the beach and enjoy it. So the distance between the wave peaks is the wavelength. Now for sound, this is going to be the tone of the sound. And if you look at instruments, the bigger the instrument, it usually has a deeper sound. And that's because the strings or the tube that the sound is going to travel through, in the case of the wind instruments, are longer. And so therefore their wavelengths are bigger, and so they can make a lower tone sound. And then the smaller the instrument, the higher the sound, because again, you have a shorter wavelength. For wavelengths, because they are lengths, we use the metric system, so we measure them in meters. For visible light, the light that gets into our eyes, wavelength is responsible for color. So when we are looking at different wavelengths, we are looking at red, orange, yellow, green, blue, but also the entire spectrum, which is radio waves, microwaves, infrared, visible light, ultraviolet, and X-rays and gamma rays. The wavelengths differentiate these waves. So light, visible light, is measured in nanometers. So 1/1 billion meters. And typical light that we can see is in the range of 400 to about 700 nanometers, or as you can see right there, meters, 10 to the -7. So there you go. And then we have what's called frequency. So as you can imagine, the frequency of the light is going to be slower the longer the distance between the peaks is, and faster the higher the shorter the distance between the peaks. So if you have a really long wavelength, you have a very, very low frequency. And then if you have a really, really short wavelength, you have a really, really high frequency. So what is frequency? Frequency is the amount of waves that pass by a certain spot in a second. And we call it our hertz, but basically it's just per seconds. Now you might have heard of Hertz. No, not the rental car company. With TVs getting fancier nowadays, you might, when you go to buy a TV, they might talk about 60 hertz, they might talk about 120 hertz, and then some TVs will even lie and say 300 hertz and whatnot. So, but basically that is how many frames the TV can show per second. So for light, for sound, I should say, sound is going to be the pitch. So the higher the frequency of the sound, the pitch changes. If you ever say like a high-pitched sound, you're basically saying that it's making that noise very, very frequently. So visible light, frequency is going to be the energy that's in the light. And so why is frequency and energy so closely related? Well, think about a sledgehammer versus a jackhammer. You're still putting energy into whatever you're hitting with either of those devices. But with the sledgehammer, you're hitting the spot with a lot of energy, but there's a lot of time in between the whacks. But with a jackhammer, you're hitting the same spot with a small amount of energy, but you're doing it a lot of times. And so you can deliver a lot more energy with the jackhammer than you can with the sledgehammer. Visible light frequency is in the 4 times 10 to the 14th or 7 times 10 to the 14th hertz. And that is 400 trillion to 700 trillion times per second. So when you are looking at visible light, the reason why it's visible light is it has enough energy to actually cause chemicals to change in your eyes. The reason why visible light is what it is because if it had any more frequency, then it would damage the things in your eyes and you couldn't see that light. Or if it had any less frequency, it wouldn't change anything in your eyes and it wouldn't create a signal. And that's why the visible light spectrum is so small for animals. When we look at the entire spectrum of light, we only see a very, very small sliver of it. It's this nice little Goldilocks zone of enough energy to cause something to happen in our chemicals in our eyes, but not so much energy that it destroys them. As you can see, we have 2 different frequencies, and what is the important difference between these waves is that the frequency here, the wavelength is very short, so the frequency is very high. And as you can see with this guy right here, this was short wavelength, high frequency, and here we have long wavelength, low frequency. Frequency has the symbol nu, which didn't get on here because it probably got messed up. So let me draw it for you. So we already have wavelength. Wavelength is lambda. And it's measured in meters or nanometers. And then we have the Greek letter nu, which is actually N, but it looks like a V with like a little ball on it. Some people kind of draw it like that. There's a bunch of different ways to draw it, but it's the Greek letter lowercase n, and it is frequency. And it has the 1/seconds, which is also called Hz or hertz. Those are the same thing. So then finally we have speed. Speed is c. Well, if you notice, if you have a distance and you have a time, then you have distance over time, and distance over time is speed. So you guys might know that there's a speed of sound. Speed of sound is what we call the sound barrier. When you start traveling faster than the speed of sound, you have to like push air out of the way faster than it can kind of move, and it causes a sonic boom. This is what we call Mach. Mach 1 in a plane is the speed of sound. If you're going Mach 2, you're going twice the speed of sound. So every single thing that travels in a wave kind of has a maximum speed limit based off of what it's traveling through. So for sound, through air, that is what we call the speed of sound most of the time. But if you've probably heard, sound actually travels faster in water. And the reason for this is that the water molecules are closer together, and so the longitudinal wave, the compression wave, can transfer that energy faster. So the speed of sound through water is different. And of course, the density of the substance changes. So the reason why light, the speed of light is so important is because light doesn't need anything to travel through. It travels through a vacuum, meaning light can exist when there's nothing else around for it to interact with. So it can go absolutely as fast as it wants. And that's exactly what it does. It goes the universal speed limit. For some reason, nothing can go faster than the speed of light. And what is that? Well, right here, it's basically rounded. It's 3 times 10 to the 8th, or 300 million meters per second. 2.96 is times 10 to the 8th is what it is more accurately. Or 186,000 miles per second. So that's really fast. That's why, you know, when you were a little kid and you were trying to open the fridge before the light turned on, you just really couldn't do it. Unless once you started to notice there was a button in there that all you had to do was press to turn the light on and off. Or if you were like me when you were a kid, you tried to turn the light switch off and get in your bed before the lights turned off. But that didn't work. And that's because speed of light is very, very fast. So what this means is that because speed is distance over time, then what the speed of light is the wavelength divided by the frequency. And this ratio of distance wavelength to frequency always comes up with the same number, 3 times 10 to the 8 meters per second. Because we deal so much in visible light, you can also write down the visible light speed limit, which is nanometers per second, 10 to the 17th. So usually when we're talking about light, we usually tend to talk about visible light because that's what our eyes can see. And that's 3 times 10 to the 17th nanometers. So all we did was convert meters to nanometers. So now that we have speed of light, wavelength, and frequency, we can talk about energy. So there's some problems on like calculating these things. There are some problems on your worksheets. I didn't ask any like calculating speed of light stuff on your quiz. So, and I probably will only put, like 1 on the test. So it's not as important, but I just wanted you to understand the concept. So anyway, we get the electromagnetic spectrum now, where we have increasing wavelength gives us lower energy and lower frequency light. And so that gives us the radio waves, the microwaves, the infrared, the ultraviolet, the X-rays, the gamma rays. And this tiny little slice right here is visible light. That's all our eyes can see right there. And even animals that have really good vision only kind of make this thing go a little bit into the infrared and go a little bit into the ultraviolet. So animals on Earth, their eyes have evolved to have a very, very narrow spectrum of light. And again, the reason for that is energy in the light. Infrared does have energy. It can heat things up, but that's all it can do, heat them up. It can't really change their chemical composition in a meaningful way. And so not a lot of infrared light you can see, but you can still transfer information on it, like heat vision and things like that. Microwaves are used in your microwave, but they're also used in Bluetooth and, well, Bluetooth's radio waves. 5G and 4G internet uses microwave signal, and some cell signals can go into the microwave range. No, that doesn't mean you're microwaving your head. They're very, very small microwaves toward the kind of radio wave spectrum right here. Radio waves are obviously TV, FM, AM, radio, all that kind of stuff. But more recently, that's going to be your Wi-Fi signal. You might have seen that there's like 2.8 and there's 5.0 Wi-Fi signals. And these are the hertz of the radio waves that are used for those Wi-Fi signals. And then, of course, when you get sunburn, the cause of the sunburn is ultraviolet. Our atmosphere is full of all kinds of chemicals like water and ozone that filter out the X-rays and the gamma rays. Otherwise, we would be dead. Gamma rays are bad news. You're not going to be able to survive that. They just have way too much energy in them. And so it's nice that they are absorbed by our atmosphere. This is why living on Mars sounds really cool, but it's going to be one of those things that's difficult because there's very little atmosphere. And therefore, if you go outside, you're going to be hit with gamma rays. So this is also a problem for flight attendants and people who work in space. The spaceships and the planes, they don't protect from X-rays and gamma rays. And so if you're a flight attendant, you're going to be exposed highly to gamma rays and X-rays, more so than even a nuclear technician. So how do we calculate the energy that light has? Well, Planck came up with a way to do it. And basically what he said was, what if we think about light like a ocean wave, where it's going to deliver a packet of energy like a wave would crash on the beach. And so the amount of packets of energy that a wave could deliver per second will be its energy. And so he came up with the equation, energy equals some amount of energy in each packet times the frequency. So the amount of times that the packet can be delivered. This goes back to our jackhammer theory. If you think about a jackhammer, if you don't have a ton of frequency, then that tiny little hammer is not going to be delivering its packet of energy, its little punch, a lot, and therefore it's not going to deliver that much energy. But if you turn on the jackhammer all the way, then it's going to deliver a lot of energy every second, and so therefore the energy is going to increase. So H is what we call Planck's constant, and it's very, very small. The amount of energy that's in each little wave of light is 6.626 times 10 to the negative 34th joules hertz. It should be joules hertz, not joules per hertz, but either way. Basically joules per second. So, or joules seconds, that's what I'm going to say, joules seconds. So joules every second. It's extremely small, but because it's extremely small, light delivers that packet extremely large amounts of time. Remember that the frequency of visible light was 400 trillion to 700 trillion. So that is how much energy it can deliver. You basically take those things and multiply them together. That's where you get the equation E equals H, nu. And so there's an example. We're not going to do that unless you have questions on it tomorrow. So basically the energy is going to be H times the frequency, where H is going to be 6.626 times 10 to the negative 34th joules seconds, or joules per hertz. Energy is measured in joules. A joule is just a measure of energy. So why did we learn all that? Well, it turns out that if we're talking about atoms, right, and here's our nucleus, the electron out here is being pulled towards the nucleus, but it doesn't fall into it. So it must be traveling in a direction that is counteracting this force, or basically an orbit. If you were standing on the Earth and you shot a gun, the bullet would go bang, 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 and it would look like it would travel in a straight line, but it would actually go boom, and hit the ground. Pretty cool. And the reason for that is the force due to gravity is pulling on the bullet. And the force that you gave the bullet is smaller than the force due to gravity. And eventually gravity wins and pulls the bullet down. So when we have an orbit, what's happening is if you could stand on a high enough position on the Earth and shoot your gun, the bullet, bang, 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 if it overcame the force due to gravity, it would shoot off into space. But guns don't have that much energy because what you need is about 17,000 miles per hour to be able to even just get into orbit around the Earth. And so what is an orbit? An orbit is when the bullet eventually has enough energy to where the force due to gravity is equal to the force forward. And what happens is it orbits. So this idea is what started people getting to talk about where the electron was. And it comes up with the idea, which is called quantum mechanics, which sounds fancy, but it's really just how electrons move around the nucleus. So Bohr, having worked with the information provided by people like Rutherford, wanted to describe where the electrons were. And what he said is that each electron must be orbiting the nucleus like the planets orbit the sun. And he used orbital mechanics, and instead of using the force of gravity, he used the attractive force between the proton and the electron to be able to describe where the electron could fit. And you came up with this very typical drawing of an atom where we have the rings around the atom where the electron could exist. And he explained Einstein's photoelectric effect as the distance between these orbits is an actual energy difference. And so when an electron moves between the orbits, it has to gain or lose electrons. He said that electrons normally would want to sit at the absolute lowest energy level, or the closest orbit, and that if they wanted to go any further out, this would be harder for them to do because one, they have to travel faster, and two, they're getting pulled away from the nucleus, and so they would have to absorb that light or that energy. When they then don't have something giving them that energy, they fall back down and they give off that energy as light. And this is the photoelectric effect. When we look at that light through a prism, we get what's called a bright line emission spectra. In the case of hydrogen, we should have two purple lines, a blue line, and a red line in the visible spectrum of light that is the energy associated with the visible spectrum. But it also gives off some ultraviolet and some infrared. And in class, I have these lamps that do this for you, but the hydrogen one gets really hot because of the infrared light that gives it off. The glass absorbs it very well. So this worked really well. Bohr's mechanical model described hydrogen perfectly. The problem is it did not describe helium. So here's that same diagram, but it's just kind of been flattened out. Whereas you can see down here, this is where the electron normally wants to be. And if it absorbs some light, each fall that it occurs, like going from 5 down to 1, results in ultraviolet, and the visible light spectrums occur from dropping from 5 to 2, from 4 to 2, and from 3 to 2. Now, in the first part of chapter 5, it talks about these M, N, and L numbers. I'm not going to bother asking you all that kind of stuff. I'm just more interested in you understanding that electrons go up in energy level when they absorb energy, and they fall back down, giving off different wavelengths of light. We can then use those wavelengths of light to calculate the energy, and from then we can then figure out where the electron is. How many electrons fit in M, N, and L? That's not really that interesting. So the problem that we had with the Bohr model is when you start looking at other substances, their bright line emission spectra did not follow his model. There's our hydrogen with our red and our green and our blue and our 2 purples. But if you look at helium, you can see it also has a red band, but it's shifted. The green band looks about where it's supposed to be, but we have a new green band and a yellow band. We got a new turquoise band. There's the blue one, but again, it shifted, and the purples seem to have just disappeared. So what's going on? The Bohr model didn't work, and that was because the electrons, to orbit around the nucleus, that was only assuming their particle nature. But we spent this entire time talking about waves. So a guy named de Broglie came in and tried to explain the wave function as the orbits are basically where the wave functions fit perfectly. But again, that didn't work for anything but hydrogen. And you probably heard this guy's name before. It was Schrodinger who came in and was able to basically describe the electron in terms of exactly what it's happening, taking account its particle and its wave nature by using what we call probability math. Remember when we talked yesterday, we talked about how a fan is 3 or 4 fan blades, and when the fan is off, you can see it where it is, and it looks like 4 or 3 fan blades. But when it's spinning, it looks like a circle. And so Schrodinger was like, okay, well, an electron is going to be moving all the time, and it's not going to need to be fixed in an orbit, but it is going to be a certain distance from the nucleus. And so it's going to have these kind of clouds or areas where you would most likely be able to find it. So the best example I can give you about the difference of this is imagine we were looking down on a map of your general area of where you live. We zoomed up, maybe flew up a mile, and say you live up here and your school's right here. If we were to take a time lapse of an entire year of your life and say we made you a nice green glowy dot, then it would be very bright at your house. And it would be very bright at your school, because the likelihood during a day that we find you at your house or at your school is extremely high. And maybe you take the same route every single day. And so we would have this kind of cloud of green light that shows you how you get from school and home. This would be your brightest time lapse. But maybe your favorite restaurant is kind of over here. And so you kind of have a slightly less bright light going to some other location. And maybe you had a relationship for a little while where you went to your boyfriend or girlfriend's house after school and they lived near to the school, but that didn't last very long, so you broke up. Or maybe you're like me and you love amusement parks, so you love getting on the freeway and going to Disneyland every weekend, so you might have another thing. Well, the idea is that every single one of you would have a different time-lapse photo if you were glowing, because you would all be doing something different with your daily lives. And this was the idea behind electrons. What Bohr found must be what most electrons do all the time. But also, because of all the other protons and all the other electrons, it must twist and change their time-lapse photo to produce the other wavelengths of light that we were seeing. Now, you'll read about it in the book where it talks about the M and the L and all that kind of stuff. But basically, what we're going to do is we're going to summarize it. And what Bohr says, or Schrodinger says, is he shortens it and he calls it quantum numbers. And he says that there are 4 principal quantum numbers. The first principal quantum number is what Bohr discovered, and this is what we usually describe as like n. But we're just not going to really get into that. And then when we're talking about a time lapse, we're talking about it making a shape. And so that is our second principal quantum number. And then if you think about shapes in 3 dimensions, every shape has a different way it looks depending on which way you're looking at it. And so that's orientation. And then finally, the direction or the spin that the electron is moving inside that shape. And so if we understand these 4 principal quantum numbers, we can describe where every single electron is in an atom, regardless if it has more protons and more electrons. So again, the principal quantum number is the amount of electrons that can fit into a particular orbit and or energy level, and it's 2n squared. So the amount of electrons that can fit in the first energy level is 1 times 2 squared. So 1 squared is 1 times 2, 2. So only 2 electrons can fit in the first energy level. This also defines the size, because the quantum number, if you've ever been to Disneyland and you've seen that they put like a balloon inside a balloon, well, each balloon is a new principal quantum number. And then we get what we call the shape. So the shape of each energy level is going to determine about how many electrons can fit in there. So for the first energy level, we only can fit 2, and so we can only fit 1 shape. But with the second energy level, 2 squared is 4 times 2 is 8. We can fit 8 electrons. And so 2 fit in the first shape and 6 fit in the second shape. The second shape is called P. The first shape is called S. Third energy level, 3 squared is 9 times 2 is 18. It can fit 18 electrons, 2 in the S, 6 in the P, and 10 in the D. The fourth energy level, 4 squared, 8. What did I do? 3 squared, 9 times 2, 18. 4 squared, 16 times 2, 32. There we go. Bad math. The fourth energy level fits 32, 2 in the S, 6 in the P, 10 in the D, and 14 in the F. Now, there are 5th, 6th, 7th energy levels, but we just run out of atoms at that point. We don't have enough electrons to fit them in. Sometimes these are called sublevels. And then if we're talking about the shape, the amount of orientations in space that this shape occurs is what we call the third principal quantum number. S is a sphere, as you can see right here. S is a sphere, and so it only has 1 orientation, because a ball is a ball no matter how you look at it. But for P, P has 3 orientations. You can think of it like holding a dumbbell. You can hold a dumbbell straight in front of you, that would be your X. You could hold it up and down, that would be your Y. And you could hold it pointing away from you, that would be the Z. Well, because of these 3 orientations in space that you can hold the dumbbell, you get the 6 areas where an electron can exist, which kind of looks like the everlasting gobstopper from the original Willy Wonka movie. For the d orbitals, they have 5 orientations. So 4 of them make sense, because what the d is that 2 dumbbells held together in an X. So if you think about an X like a sheet of paper, you can hold the sheet of paper in the 4 different planes. So you can hold it up like this. You could turn it sideways. You could lay it flat. And then, of course, you could turn it and lay it flat the other way. The weird thing happens with the fifth orientation. Basically, one of the dumbbells kind of wraps around itself and it kind of makes this weird donut shape. And the s orbitals are a little bit even more difficult, or sorry, the f orbitals are even more difficult to describe. There's a couple that kind of look like everlasting gobstoppers, and then I think these look like candy bracelets. And then, of course, we have this weird one here with the double donut. So these orientations, each orientation can fit 2 electrons. That's why S can only fit 2 electrons because it only has 1 orientation. P can fit 6 electrons because it has 6 lobes in 3 orientations. And D can fit 10 because it has 5 orientations, and each dumbbell is an electron, so 1 electron here, 1 electron there. And remember what these are, these balloons here, these shapes, are where you could find the electron. They're a time lapse of where the electron could be. If you were to sit there and grab the electron like you did if you put your hand in the fan blade, you would grab the electron and it wouldn't look like this. It wouldn't be a dumbbell. It would be a tiny speck. But if you were looking at an atom, the sphere of influence that that electron takes up in a d orbital is right here. Right there, it's buzzing around inside that cloud. And the other electron is buzzing around inside this cloud. So this gives us all the possibilities of the shapes of the electron clouds. S's are spheres, P's are dumbbells, D's are weird double dumbbells and donuts, and then F's are weird candy bracelets, everlasting godstoppers, and double donuts. It's, again, spheres of influence. Just like your time-lapse photo would be very weird. So finally, each orientation fits 2 electrons because they have to spin in opposite directions. Now, why do they have to do that? Remember that electrons don't like each other. So imagine you are spinning around in a circle, going in this direction. If another electron was in this same space, spinning around in the same direction as you, you might run into each other. Say the first electron is right here and the other electron's over here. You're getting really close to each other and you're kind of sitting there close to each other depending on how fast you're moving. And say, for instance, this electron is moving faster than that one. Well, it's going to be very, very close to each other. And that's going to push on each other. They're not going to want to be near each other. But if you're spinning in opposite directions, then you're only going to be near each other for a very short amount of time. So the reason why only 2 electrons fit in each orientation is because they have to spin opposite of each other so that way they interact as little as possible. As soon as you introduce the third electron, you can no longer minimize your interaction, and therefore you have to move up into a higher energy level because sitting at the higher orbit is better than trying to fight the negative repulsion force. So I wanted to show you something real quick. Notice that the S has 1 orientation or 1 orbit. It fits 2 electrons. P has 3, it fits 6. D has 5, it fits 10. And F has 7, it fits 14. If we go to the periodic table, now we'll go to a different, open a new tab. Google periodic table, images. Now we'll just use this one right here. All right. We're gonna take a snapshot. Go away. Anyway, if we look at the screen here, you'll notice that this area right here, this little tower of atoms, is 2 columns high. And if we go over here and we look at this columns over here, you'll notice that they are 6 columns. And if you look at the middle, guess what? 10. And if you go down here, 14. The periodic table was originally arranged in the 1850s, before they even knew what protons, neutrons, electrons were. But it turns out what they were doing was they were actually organizing the periodic table based off of the electron configuration, or where the electrons are. Pretty cool. So let's talk about writing electron configurations. Okay. So when we talk about an atom, we want to talk about where its electrons are. Well, what we could do is we could use what's called an orbital diagram. Orbital diagram. And an orbital diagram depends on how you want to look at it. Some people draw it like this. Some people draw it like that. The most famous one that I use all the time is like this, where we have flipped over, where we have the 1s on the bottom, like that. There we go. Where each one of these little places is a place where you can put your electrons. So in the first energy level, sorry, my computer is lagging. In the first energy level, we have only the S, so we can fit 2 electrons here. In the second energy level, we have the P and the S, so we can fit both. So when it comes to writing our electron configuration, if we wanted to write the electron configuration for hydrogen, hydrogen only has 1 electron. So hydrogen, we can drop our little guy in here, and we're going to draw an arrow just to represent the electron. Hydrogen would have 1s1 as its electron configuration because it only has 1 electron. But if we were to do helium, helium has 2 electrons. So we would put 1 there, and then we would draw an opposite arrow down, and that would give us 1s2. If we go to the very next element on the periodic table, we go to lithium. Lithium has 3 electrons, so 1 here, 1 there, and then 1 there, to give us 1s2, 2s1. The very next element on the periodic table, beryllium, has 4 electrons, 1, 2, 3, 4, 1s2, 2s2. Carbon, 1s2, 2s2. Just like before, but now we're going to put 1 here. The rules that we're following here to fill in our orbital diagram are called Hund's rule, the Aufbau principle, and what's the other one? The Pauli exclusion principle. So The Aufbau principle states that the electrons have to go all the way to the bottom first. They want to occupy the lowest energy level first. And I call this the Plinko rule or the Connect 4 rule, where if you drop the checker into the board, it's got to go all the way to the bottom first. And then we have the Pauli exclusion principle. And the Pauli exclusion principle states that electrons have to basically be in opposite spin states. So that's why we're drawing them in up and down arrows. When we write nitrogen's electron configuration, we don't see Hund's rule yet. It's not until, what am I skipping? Boron. I skipped boron, sorry. This is boron. This is carbon. That's carbon. 2p2. Boron, which I skipped, 1s2, 2s2, 2p1. You'll notice that Hund's rule is going to kick in right here. And what Hund's rule states is if they have the same number of energy to be in that orbital, then why would the electrons be in the same orientation as each other? They would occupy a different orientation. Same thing goes for nitrogen. Nitrogen's electron will go there to give us 1s2, 2s2, 2p3. And it's not until oxygen that they start going into the same orbitals as each other again. Fluorine, 1s2, 2s2, 2p6, or 5. And then finally, neon, the noble gas, 1s2, 2s2, 2p6. Now we can just keep doing this forever and ever and ever until we run out of atoms at 120 electrons. That would be the 7p6 way up there at the top. Which is cut off because of the drawing here. But this is an electron configuration. This tells us where every single electron is on an atom. Now there's another way to do it. You can also use the periodic table. So here is a good example of a periodic table. Don't open it again. Oh, you booger. All right. So here is the periodic table split into the 4 orbital regions: the S block, the P block, the D block, and the F block. And we can use the periodic table to also write electron configurations. Let me move that out of the way and do a different snippet. Sorry. I keep that open so I can admit you guys if you get dropped out. All right. So if we look at the periodic table here, we can use the periodic table to write electron configurations. Each one of these rows here is the number 1, just like on the orbital diagram. So if we have hydrogen and we want to write its electron configuration, we're in row 1, we're in the S block, and we're in the first position, 1s1. If we want to do helium, helium is an exception because it's over here. It looks like it's in the P block, but they colored it to show you it's actually right there. So that gives us helium as 1s2 because we're in the first row in the S block in the second position. If you remember, lithium was 1s2, 2s1. Well, you'll notice that we had to go 1s2, and now we do 2s1, just like that. So say, for instance, we wanted to write the electron configuration of iron down here. Well, if we go to our orbital diagram, iron is number 26 on the periodic table. So that means we have 26 electrons to put in here. And when we left off at number 10. Come on, erase faster. So there's number 10. So let's go number 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So that gives us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and notice that it actually goes back to 3 and says 3d, and in this case we have 6 there. This is exactly what is shown on the periodic table as well. The problem is that the D block doesn't show up until the 4th row. The reason for this is what we call electron shielding. Even though the third shape should have showed up in the 3rd energy level, because there's so many electrons starting to fill up, it doesn't actually have enough energy to fit until the 4th energy level. So that's why 3D exists as the 4th row. So you just have to remember that this is line 4, but this is actually 3D, 4D, 5D, and 6D. And the same thing happens for the F block, which is right here and right here. This is actually 4F and 5F, because the Fs should have showed up in row 4, but they don't show up till row 6. So we can do the exact same thing we did before. We can do if we're doing iron here, iron, we can say 1s and we go twice, so 1s2. And then we can do 2s twice, so 2s2. Then we can do 2p 6 times, 2p6. Then we can do 3s2. Then we can do 3p6. And then we can do 4s2. And then we're going to go through 3d, but we're only going to go through 6 of them. So we go 3d6. And so this is how you can use the periodic table to write electron configurations. Pretty simple. Now, as you can tell, it's going to get kind of tedious going into some of the later elements. Say, for instance, you were even just trying to do 10 down there with 50 electrons. Well, we're left off at 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. So this is iron. So for tin, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and I even have to write on the next line. And then we have 5s2, 4d10, 5p2. So as you can see, it gets to be very, very tedious to write these. So there is a way to abbreviate them, and that is to use noble gases. So the noble gases are, you probably already know, the noble gases are over here in group 18 on the periodic table, or group 8A. And they end each row of the periodic table. Helium is the end of row 1. Neon, the end of row 2, argon, the end of row 3, krypton, xenon, radon. This is actually Augustin, which is named after a Russian scientist, but it's not on there because it's the absolute end of the periodic table. So if we wanted to write 10, rather than writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2 for tin. Tin is in the 5th row. So rather than writing all of this, that is krypton. So rather than writing all that, we can write tin equals krypton, and then just write what's left over. 5s2, because we're right there with 5s2. 4d10, because we're going through 4d10. And then 5p2. It makes it a lot shorter. And when we talk on Friday, it will show us the valence electrons, which are the most important electrons for the atom. So this is how we write electron configurations. My lecture's already kind of gone an hour and 15 minutes, so I don't want to go too much more. There's lots of more resources on there. I recommend going through and watching those. They're shorter, 5-10 minutes, help you out with those types of things. Working through the worksheets helps, but also if you want to bring up the quiz and work through the quiz and do it that way, that's fine too, because remember, you can retake the quizzes. So that was a lot, and so I'm going to leave you with that for now. And then we'll come back and answer questions after you guys have kind of got in.